get started recording. So we looked at the carbonyl. Yes? Oh, yeah, good call. The asterisks mean that they're harder questions. Okay. So I fully don't expect everybody to complete those correctly. What I do expect is you to attempt them and see what's going on with them. If you can solve them really quickly because you think they're easy, great. I looked at them and I thought they were hard. So,
let's make it an up question.
I can't do anything about that, actually. Sorry. It just looked like an interesting question to me.
Just make it 29 and 17.
Those weren't interesting.
They're easier to solve.
So, back with our carbonyl. So with the chemistry with our carbonyls, we were looking at the reactivity of this functional group. So we talked about it, and we said, what reactivity are we looking for?
Pi bond.
Okay, so we said the pi bond was a big source of reactivity, but it's not going to be the same reactivity as we might expect for the alkene. Why is it not drawing? Sorry, wrong screen. There we go. We might predict that for our alkene, and the issue of why it's not the same reactivity as for an alkene is in an alkene it's carbon-carbon double bonds, right? Okay, so there was no polarity associated with that bond. When we move to the carbonyl, we've got the oxygen now that changes the character of that pi bond, and we end up seeing the electron density shift up onto the oxygen a little bit more, which then means our oxygen starts to build what charge? Negative. Starts to build a negative. What kind of species are negative? Good, we get nucleophiles. What else? Well, you can say them faster than I can say it. Lewis, base, what else? And we get our Bronsted bases as well, right? Okay, so those are all the possible chemistries that we might see coming out of the carbonyl oxygen. Okay, or at the same time, what happens to the carbon at the bottom of that? It's now going to become partially positive because it's now lost electrons. What kind of species are partially positive?
Electrophiles.
That's where we get our electrophiles. I'm just going to abbreviate now on the last one. Bronsted acid. Why can't it be a Bronsted acid? No hydrogen on that carbon. Okay, so we're looking at a Lewis acid. If we were now going to decide between these two, the positive or the negative, which one would we predict to be more reactive? Okay. The positive carbon, not the negative oxygen. Why not the negative oxygen? Oxygen's very electronegative. It wants to hold that charge. Okay, it doesn't want to let go of it. Okay, so it's going to hold on to that. So we would expect our reactivity for our carbonyls to focus around that carbon. Okay, I carefully chose the location of that arrow. What would react with the electrophile? Nucleophiles. Okay, and just like we did with our oxygen above, if it's a nucleophile, what are the red flags that we'd be looking for? A negative charge. So ultimately, it's a source of electrons. Okay. So when we went through and discussed this on Tuesday, we said our nucleophile choices, we pretty much had oxygen, nitrogen, and carbon. Okay, we're going to add another one probably next week, but we started with the oxygen, which arguably I think is the hardest one to deal with. Okay, so when we went through and talked about it, I drew everything out by hand. I forgot I added an extra little thing here. To slow down our reaction, when we're looking at the oxygen reaction, let's break it into the individual pieces. So we can start with our carbonyl again. Let me go ahead and draw in the carbon. And in the first step of it reacting with an oxygen nucleophile, we end up forming the hemiacetal. Okay? And we end up with a product. Let me color code that. Whoops, that's an eraser. We've got our oxygen hydrogen, so we can pick up a hydrogen from our solvent. And one of the things that we would react with in the middle there would be some OR containing species. I'm going to leave off the charge and leave off that. Well, let's go ahead and put the hydrogen on there. Okay? And in the process of our first step, our hydrogen attaches to the oxygen from our carbonyl, and we end up putting the OR to the carbon. Okay? So this format is our hemiacetal, where we've got that central carbon, tetrahedral carbon, where one of the oxygens is an alcohol and the other one's an OR. Okay, so we end up with an ether functionality and an alcohol functionality. Okay? We can take this into a second step of the reaction. We'll still have our carbon, and what we'll end up doing is fully substituting out our oxygen, and we end up with OR, OR, and we can kick off, ultimately becomes H2O. Okay? So one of the things that is most commonly left out of these mechanisms, and you can see I already did it, is where did that second OR come from? More of the initial to begin with. So when we're discussing these reactions, you have to realize we're looking at a lot of these things in solution. It's no longer a one-for-one trade, which we could do for substitution reactions or the addition. We could look at an individual molecule of one type and an individual of the other and react them. Now we're looking at bulk solutions. We get rid of the numbers and we just kind of have to assume that something is there to continue the reaction along. Okay? This reaction, going from the carbonyl all the way to the acetal, there's two primary mechanisms by which it can occur. We can either get base catalyst, which is what we talked about before, and we picked the base catalyst because our nucleophile in this case ends up being OR minus. And we started with the base catalyst because that gives us that negative charge, a good strong nucleophile. So it's easier for us to see, so that's where we started with. Okay? The other option is looking at an acid catalyst. Okay? So let's go ahead and now take a look at these. As I promised, I went through and got these drawn up digitally so you can take a look at them. So we start off with our carbonyl at the very beginning. I'll try and highlight it as we go through it. We've got our carbonyl that reacts with our nucleophile. We know it's the nucleophile because it's negatively charged. Our carbonyl then acts as the electrophile. Okay. After the first step of that reaction, the electrons from that oxygen come in, share with our carbonyl. That means that carbon has now gained a bond. That carbon would now have too many bonds, so we have to break a bond. The easiest bond to break will be the pi bond. So we can see those electrons shift up onto the upper oxygen. Okay? We draw the product of that reaction, which is what we see here. Okay? That reaction can go through another step, and we'll go through that extra acid-base step just so that we can see the hemiacetal formation. Okay? So we've got more alcohol floating around in solution. Our alkoxide can pick up a hydrogen, and we end up with our hemiacetal intermediate. Okay? So our first step was kind of a electrophile-nucleophile reaction followed by an acid-base reaction. Okay? If we now move down below to the second section, okay, so this we could say is part 1 for the formation of our hemiacetal, part 2 moving to the acetal. Okay? We tried to go through this mechanism before as well. So if we start here, this carbon is still fairly unstable. Why is it unstable?
2 oxygens.
It's got 2 very electronegative oxygens attached to it, meaning it's very partially positive. It is susceptible to another nucleophilic attack. So we could take another ethanolic or alcoholic oxide. That can go in and attack that carbon. It'll kick out the best leaving group, which in this case is our hydroxide. Okay? And that produces our acetal product, and I left that product off, our hydroxide ion. Okay? You'll notice that I then ask a question up there. Why is this not a very likely step? So we've got a bunch of possible answers for this. I heard probably the primary one. Sterics. What type of mechanism is this really undergoing? It's a little bit trickier. It's a substitution. What type of substitution? We've got a nucleophile. How many steps? It's all happening in one step for our substitution, which means we're looking at SN2. I know it was kind of a misleading clue. Okay? 2 species are involved in that step, so we end up with an SN2 mechanism. When we think back all the way back to our substitution reactions, the SN2 reaction, what controlled it? Sterics. Okay? We wanted the minimal amount of crowding around that nucleophile, or our electrophile, okay, where our substitution was occurring. We've got an awful lot of things crowding that position. We've got 2 oxygens and 2 carbons. Sterically, that position is extremely blocked. Okay? So that would suggest that this step is not particularly likely, which we could show by using our equilibrium arrows, with the smaller arrow going towards our product, the bigger arrow going back to our hemiacetal. Okay? So when we're looking at acetal formation, the based catalyst is not the most common one because it kind of stalls out at the hemiacetal. We don't get a lot of production pushing all the way towards that acetal formation. Okay? Questions about that? Okay. So the other thing we talked about was the hydrolysis. So one of the useful things when we're looking at these acetal formations is that it's a reversible reaction. It's both a problem and reversible. Okay, so if we go back to this, okay, in the process of doing this reaction, going from here, going from our carbonyl to our hemiacetal, we'll ignore the acetal formation because we said that's not very favorable. Those are all equilibrium steps, which means when we put this reaction mixture together, we're going to get a mixture of both our carbonyl and the hemiacetal product. If we want just the hemiacetal, okay, first off, it's not going to happen, okay, because our hemiacetal is actually more unstable than our carbonyl. Okay. How can we try to push it as much as possible to the hemiacetal? That's where we talked about the funny French man. I think he's French. We can add a ton of one of these reagents, okay, which goes back to Le Chatelier's principle. Okay, so if we had a reaction at equilibrium, our balance is set. Okay, what we want to do is shift our equilibrium to produce as much products as possible. Okay, so what we can do is add a whole bunch of reactants. That shifts the balance towards our reactants. Well, equilibrium in Le Chatelier says we need to alleviate that stress, and it shifts to try and form more products to counteract that balance. Okay? So by adding more of one of our starting materials, we can try and force the formation of the hemiacetal, okay, through Le Chatelier's principle. Does that kind of make sense? Okay? So the other big piece that's helpful for this is we do get an equilibrium reaction. So once we form the acetal or hemiacetal, we can always take it apart and go back to our carbonyl. Okay? We talked briefly about why that's helpful, and we'll come back to that in a second too. Okay? So if we go through and look at the reversibility, if we start at the acetal, okay, dang it. If we start at the acetal, what we're going to try and do is reverse the reaction in the other direction. We're going to again start with a base. Okay? This time our base, instead of being an alcohol or an RO, we're trying to get rid of those R groups. So we're going to add a hydroxide, okay, a nice strong base. That base can act as a nucleophile. Why can it act as a nucleophile? Because it's negatively charged. Okay? It's a good source of electrons. Our carbon in the middle is still reactive. Why?
Two electronegative elements.
Still two electronegative elements. So our base could come in, attack that carbon, except our carbon would now have 5 bonds. We have to break a bond. In this case, we don't have any easy pi bonds. We'll have to break a sigma bond. Do we break one bond to our oxygen, or do we break the bond to our carbons? Why to the oxygen? Oxygen's more electronegative. It's willing to take the electrons. Whereas the carbon-carbon bond, no difference in electronegativity. We don't expect that carbon to take the electrons with it.
Does it matter which oxygen?
Is there a difference between those two? No. So it's not going to matter in this case. And remember, depending on which one you decided to draw, it may look different than what's drawn. But if you remember back to stereochemistry, we could run the same analogy as what was my name?
Mike.
And still Mike. So if we flip the molecule, rotate it, it's still the same molecule. Okay, so we can still get away with making it look slightly different as we go through it. Okay, as long as we don't change any of the sigma bond structure. We end up with, after that very first step, the hemiacetal. Okay, how do we know it's the hemiacetal? We look for our carbon that has 2 oxygens bound to it. Okay, we then evaluate what's attached to those oxygens. In this case, it's an R group, which is giving us that acetal. The hydrogen is where we're getting that hemi from. Hey, H-hemi, hydrogen. There we go. Nice, easy way to remember it. Okay? At that point, we're still not all the way back to the carbonyl. We're still in a basic solution. So our next step of the reaction is to take more of our base or nucleophile and have it pull off the hydrogen on that oxygen. Okay? Because that's a relatively acidic hydrogen. So we perform another acid-base reaction. Okay? Which then takes us to a very simple step, or that step was simple. And we now end up at that intermediate. That negative charge, not particularly stable. Why? No. Because it's charged. I know, it's repeating the same thing I said. Okay? So it's charged, that's a problem. We still have that partially positive carbon, which is still potentially reactive. So we can take that negative and start to share it with our positive, and we can start to form our double bond. Except, how many bonds would we then have? 5 bonds again. So what do we have to do? Break a bond. Which of those bonds is the easiest to break? Our carbon-oxygen. Okay? And what we end up with at the very end is the carbonyl that we started with all the way back at the very beginning, and our base. Okay, or our base catalyst. Okay? So the idea with these is you can use your acetal or hemiacetal to change the functionality of your structure. You're changing it from being a carbonyl into, say, an alcohol or an ether. Okay? So we want to take advantage of that chemistry to kind of simplify things. Okay? But before we even get into that, okay, we said the base catalyst was not the best because we can't get it all the way to the acetal easily. Okay? Because of that harsh SN2 reaction going that way. Right? So let's try a different catalyst. So what we can go through and try and do is use an acid catalyst. Okay, this time, unfortunately with the acids, you get a lot more protonation, deprotonations, which is why this is coming out as a lot more steps. Okay, this is why I like to hand draw it so we don't get confused. So let's start simple. Up at our carbonyl. Whoops. Up at our carbonyl. Okay. If we look at the reactivity of that carbonyl, we still have the oxygen being a Lewis base, Bronsted base, all that fun stuff. And we still have our carbon being a reasonable electrophile and Lewis acid. Okay. So in our base catalyst, we had a reasonable nucleophile to react with our Lewis acid or our electrophile. Except in this case, we're now changing our reaction. So we can pull the famous face test, as bad as it may sound. We can start with our carbonyl versus this species. What is our reagent here? H3O plus, also known as, which acts as an acid. So if we pull a face test on this, which would you rather have in your face? Carbonyl, which we don't really know a whole lot about its chemistry, or acid? Carbonyl. Probably the carbonyl. Okay, so the acid's much more reactive. So let's think about what's reactive about the acid. So what concerns you? The OH2 part or the H+? Well, what is OH2? Water. Are we really concerned about water in the face? No. So it's probably the hydrogen of that. And that's going to be our H+. So even though the positive charge is on the oxygen, the most positive atom there is our hydrogen. If that hydrogen is partially positive, how can I stabilize it? I need to give it electrons. Where do I have electrons? On the oxygen. Okay? So we can use the Bronsted base characteristics of our oxygen to react with our acid in an acid-base type reaction. Okay? So we can then look at the products of that reaction. Sorry, I didn't draw H2O, so let me add that back up there. Okay? And we now have our carbonyl with a positive charge on that oxygen. Does oxygen want to be positively charged? No. So what is oxygen going to want to do? It's going to want to steal electrons from something. Okay? I'm going to draw this as a secondary thing. I thought I had a little more space than I did. Okay, where can it get electrons from the easiest? Is there an easier place? Probably from the hydrogen. If it takes it from the hydrogen, what happens? It goes backwards, and we get the reverse reaction. Remember, it's an equilibrium. All of these reactions are happening simultaneously. So what we need to do is look for another source to see if there's another possibility. Could it get it from the pi bond? Yeah. So let's take the electrons from that pi bond. So we'll just look at that arrow for the moment. Ignore the bottom ones. Ignore that guy. What happens? Oxygen picks up its lone pair. It still has the bond to the hydrogen. What happened to our carbon?
It lost.
It lost electrons, so it's now positive. What did our acid catalyst do in this reaction? How did it make it more reactive? It made our electrophile more electrophilic by putting a formal positive charge on that atom where we really didn't have a positive charge to begin with. Okay? So our acid is helping facilitate the reaction by making our electrophile a little bit more reactive. Okay? So if we go back, whoops, eraser. If we go back to our reaction, that carbon is now extremely positive. We want to stabilize that. What do we have floating around in solution? This is where we also have an alcohol solvent. Okay? That alcohol has electrons on the oxygen. That oxygen can act as, rhymes with electrophile. It can act as a nucleophile. Okay? Those electrons can be donated back to that carbon, forming a new bond. Okay? In the process, we have to break the bond between the carbon and the oxygen. Those electrons will shift up onto the oxygen, and we end up with an intermediate. Okay? That intermediate starts to look an awful lot like our hemiacetal, except the alcohol that we put in there to begin with, that oxygen is positively charged. Does oxygen want to be positive? No. What's it going to do? Take electrons. Where's the easiest place to get electrons from? Probably from the hydrogen. We could also go all the way back to it coming from the carbon. If we did that, what happens? We reverse the reaction. Okay? So if it pulls it from the hydrogen, most people like to have something come and pick up the hydrogen. I don't require it, but since most people show it, there it is. We could add that in there and have another molecule of ethanol pick up that hydrogen. The result of that reaction gives us our hemiacetal. What type of reaction was that last one? Acid-base. Okay. This species right there, that hydrogen, was very, very positive. An awful lot like a proton. Okay. So our intermediate acts as a proton donor. Our ethanol acts as a proton acceptor, and we get an acid-base reaction. Okay. And we now have our hemiacetal. The nice thing about our acidic solution is that we can then continue on. So we take a look at our hemiacetal. We still have a lot of electrons on our hemiacetal. We could add a hydrogen or have those oxygens act as bases to pick up a hydrogen. And we could have the one that we just put on act as a base to pick up a hydrogen. But what does that do? That again takes us the reverse direction. So what we're going to do is trying to focus that we're moving forward always towards the acetal. We'll have the other oxygen react. Okay, it'll pick up another hydrogen from our... No. Do you have any idea why that happens? It just turned off. Yeah, it died at the end of class. Go ahead and resume. So, what else could we end up doing with this? So now I've got a bunch of pictures. So again, I haven't had time to draw these on here digitally, so we'll do it by hand. So, come back here. If we had this compound? Acetal, hemiacetal? Or none of the above?
Yes.
What do we need to look for? We need to look for a carbon that has oxygens bound to it. So there's that carbon with oxygen and an oxygen. So we do have our two oxygens bound to a single carbon. That's a good first step. The next part is deciding what are those oxygens bound to. Carbon, carbon. We're looking at an acetal. Okay? So the next fun part about this. Where did this acetal come from? Okay. So this is where we've got to be real careful with how these things came apart. So if we go through the mechanism and evaluate where each of those bonds are breaking and forming, okay, hopefully what you'll start to notice is that the bonds that are breaking and forming are now here in green. Okay? So those two new bonds were formed in the process of forming this acetal. Yes?
So it came from a cyclohexanone?
So what we started with, yes, but I'm going to go a little bit slower than that. We're going to break off this piece and this piece. We said our acid catalyst was going to be the best option, so one of the things that were somehow run through this was an OCH3. If we made it a negative, that would be base catalyzed. So it's probably not negative, it's going to be... Can't really make it positive either. Neutral, how do we make OCH3 negative, neutral?
Give it double bond.
Give it a hydrogen. Acid catalyzed. Okay, we're looking at methanol being added as our alcohol. Okay, if we go back and now look at the other piece, none of the other sigma structure changed. So at very least, we have to have that cyclohexane. Okay? But for this oxygen to react with that top carbon has to be what kind of a charge? Has to be partially positive. It's definitely not positive now. So how can I get that oxygen or carbon to be partially positive? I probably want to put an oxygen to it. But if we only did one, it's only partially positive, so let's make it even more reactive and more relevant to, say, Chapter 13, which was the Carbonyl chapter. Turn it into a double bond. This acetal came from cyclohexanone. So we got the cyclo-hex for 6 carbons and the ONE ending, because we've got the ketone in the middle, reacting with methanol to form our acetal. Okay? So the questions that you could see would be given an individual structure, acetal, hemiacetal, or none of the above. Okay? Then I could also potentially ask, what was the alcohol added to make that acetal? So in this case, it would be methanol. Or we could take it even further, what was the starting ketone? Or all of the above. Okay, so lots of possible questions as far as representing through that. Can I clear that? So another one, let's make it more difficult. I mean, why not, right? Let's take a look at this. What do you think I'm about to draw?
Sure.
Chair, everybody's favorite. Here we go, chairs.
I don't think it is, actually. For sure we
That was worth a shot. To know. Acetal, hemiacetal, none of the above. So we want to find a carbon that is bound to oxygen. So there's a carbon bound to an oxygen. For it to be an acetal or hemiacetal, it has to be bound to 2 oxygens. Is that carbon bound to 2 oxygens? Nope, so that's not valid. So let's try again. How about that carbon? We've got 1 oxygen there, 1 oxygen there. So we are looking at some type of acetal, hemi or full. So now we got to describe or decide, is it full or not? Well, what are those oxygens bound to? Carbon and carbon. Do we have a hydrogen? Nope, which means it's an acetal. Okay? This one's a lot trickier to break apart. Well, let's go ahead and try and do it anyway, just because it's fun. What were the bonds that we made in the process of doing this, forming this acetal? You have a question?
Yeah. Why is that carbon not added to hydrogen bonds?
No, we're, sorry. So when we stepwise through that, first thing we got to do is find our carbon that has 2 oxygens. So that's where we went through. See if I can color code this. We'll start with green. We found our carbon that has 2 oxygens attached to it. So then we're now move out to the oxygens. And we now want to see what the oxygens are attached to. The oxygens are now attached to carbons. Do the oxygens have hydrogens attached to them? Do the oxygens have hydrogens? The oxygen is bound to a carbon and a carbon. Can oxygen have more than 2 bonds? No. So it's going to be the full acetal. Does that make sense? Okay. So, bonds that were made in the process of forming this acetal. Okay. That's where our acetal forms. So if we now try and break this apart, there's a couple ways that we could do it. We can guarantee the way your textbook's going to show you do it is they're going to unfold that whole thing out into a nice straight line. Problem with unfolding it out into a nice straight line? How many of you can visualize breaking those bonds, adding the new oxygens to it, and then unfolding it all in one single step? I know I'd have a hard time with it. Okay? So instead of trying to draw what the textbook asks, focus on just where the bonds break. Okay, so we've got our oxygen. That's going to get really crowded. Which goes up to our carbon, comes down to a carbon, out, carbon. There's our special carbon. We decided to break, since it's all Christmas colored, let's go ahead and do that too. So there's our special carbon there. We decided to break the 2 oxygen bonds next to it. Okay? So these 2 oxygens, see if I can star them. These 2 oxygens are what came in and reacted with this carbon. That carbon had to be what charge for those oxygens to react? Positive. So what does that mean we need on that carbon? A charge. How can we get a positive charge on that carbon? We can add our carbonyl to that position. How do we fix our hydrogen up top? Okay. If we're going to break that bond between our carbon and our oxygen, where are the electrons in that bond more than likely going to go? To the oxygen. What charge would that oxygen be? Negative. We're running a neutral product. How can we neutralize that negative oxygen? We'll put a hydrogen on it. Okay. What's the last piece missing here? Our OCH3. Where did the electrons in that bond go? To the oxygen, making the oxygen negative. How do we neutralize that? Give it a hydrogen. So what alcohol did I add in this case? Sneaky question. There's 2 of them. I added the methanol, and I had an alcohol in the back of that main structure. The answer that you would more than likely see would be, so first off, your methanol, but in the textbook, as far as the structure that they would draw, let's see if I can count this out. We got 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. There's a carbonyl and alcohol. I know that's kind of sloppy. It was zoomed out. You guys see that? Let's make sure I count it. 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5 carbons. There's the alcohol. There's my aldehyde. You guys see it? So you can jump to that final answer, seeing the whole thing unfolding, if you can do that in your head. Okay? Most students have problems with manipulating these structures in 3 dimensions. Okay, we've already seen that with chapter 6. Was it 6? Stereochemistry? Yeah. So that can be a pain to deal with. So break it into smaller steps. You don't have to flip and rotate it out to make it look pretty. Make it look ugly. If you got time, come back, make it look pretty. Yes?
If you were given this question and asked what, would you be asking what 2 alcohols were used?
What I would probably ask in this question is, how was this acetal made? Where did it come from? So for that answer, you would have to specify the structure that was drawn very cruddily up there and our OCH3. You would need to specify all of those pieces, because you needed both of those. I would probably not ask nomenclature. Okay, remember, I'm not a fan of nomenclature because I'm terrible at it. So we separate that, and I'll only ask nomenclature as a nomenclature question. Okay? Questions about acetals and hemiacetals? I think I'll write a quiz that'll give you a few more problems on that, because the rest of the problems I've got are all directly from your homework. Okay? So you can practice those identifying acetals and hemiacetals by looking at your homework assignment. Before we actually completely leave this, I really want to take a look at carbons being nucleophiles, okay, just to get this started. Okay. For it to be a nucleophile, what charge does our atom need to be? Nucleophiles are electron donors, which means we somehow need to build a negative charge on a carbon. Have we ever seen negative charge on carbon? There's been one case. No one was really happy when I did it. Remember, there was that big, long step. How do we go from this point to this point? I had a whole bunch of death stares. I can react this with sodium amide. The amide is a strong enough base, and our alkyne is a strong enough acid that we can end up with a negative carbon. So we have seen positions where carbon can act as a nucleophile, but it is extremely rare. We've seen it in acetylene, or this molecule, and you'll also see it in a new structure that we're going to evaluate. I'm just going to draw out the reaction real quickly for it so you can see it being generated, but we'll talk about it next week. What we're looking at for this class of reaction is what's referred to as, just for giggles, how do you pronounce that?
Grignard.
Oh, okay, well, that's not very fun.
Gundam?
There we go, yeah, that sounds better. Grignard reactions, or Grignard reagents. So what we're going to do, the classic example is taking something like benzene, okay, bromobenzene. What charge is on our carbon? Where's the most reactive carbon in there? Probably attached to the bromine. What charge do you think is building on that bromine? Partially positive. What did we need it to be? Negative. Okay, so we have to somehow get electrons into this structure, but what do we know about electrons? They're negative and they're mean little evil things, which means they're not particularly stable. We can't just throw electrons at it. We have to come up with a source. What we can end up doing is adding a source like magnesium metal. Not magnesium ion, but magnesium metal. It comes in with 2 electrons. In the process of this reaction, we end up forming a slightly new species. What charge is bromide in this structure? Negative. We're looking at an ionic bond, metal to nonmetal. Bromide would be negative. How much negative? 1, 2, 50? Negative 1. What's the charge on magnesium? Okay, now it has to be an ion because it's bound to some nonmetal. So it's no longer in its elemental state. What's the charge on magnesium ion? Plus 2. This structure is neutral. What charge is that carbon? we can treat that carbon as being a -1. Okay? That bond between the carbon and the magnesium is an ionic bond, very, very weak. The electrons spend most of their time on the carbon, okay, because while carbon may not be super electronegative compared to the rest of the nonmetals, compared to a metal, it's a lot more electronegative. It'll take the electrons, and what we end up equating this structure to as far as reactivity is this guy with a lone pair on that carbon and a negative charge. This species, technically with the magnesium and the bromine, is known as the Grignard reagent. We now have a negatively charged carbon, which is a nucleophile. What can that nucleophile do? React with electrophiles like our carbonyl carbons. Okay? That's some of the chemistry that we'll go through on Tuesday. We'll probably get into the nitrogens, because I don't think we'll have as short of a class then. So we'll cover the rest of carbons as nucleophiles, nitrogens as nucleophiles. I thought there was one more thing on here.
We have class on Thursday, right?
And we do have class on Thursday, yes.
None of that reading day stuff here?
Wednesday is reading day.
What?
ASU.
Did I get that wrong? We do have class next Thursday, right?
Oh, yeah.
Okay.
We don't have reading days.
Okay.
You can come in if you want, but no class.
So yeah, we will have 2 classes next week. We'll probably finish up chapter 13, and then we'll have the exam the following week.
No, I meant, well, that's,
Mike,
not in any of these pictures.
you'll be able to turn in the final to the testing center, right? So I can take it on Friday.
Nice.
I have Army training in Wisconsin
I made that
the whole week of finals. So I have to take all my final tests Friday.
Yes, I can do that. Email me, please. I've been spacing everything that's been told me.
Can do it right now.
And if you can, be even more persistent. Like this weekend, Sunday night, is that my exam yet? And then next Tuesday, that's my exam, right? Because I will end up
I highlighted all